If you pull a guitar string sideways and let it go, the restoring force pulls it back. It overshoots, returns, and oscillates. This is what we call simple harmonic motion. Now, shrink that down to the atomic scale. Think of a diatomic molecule vibrating, or an electron trapped in an atomic well. The physical reality of these systems looks nothing like a metal wire under tension. Yet, despite the massive difference in scale, physicists use the exact same mathematical foundation to describe both the guitar string and the trapped electron. The reason lies in the geometry of stability. Take any smooth potential energy curve and run a Taylor expansion around its local minimum. The first derivative vanishes, leaving a quadratic term as the dominant feature. Zoom in close enough and every stable equilibrium looks like a parabola. This geometric fact gives us the Hamiltonian for the quantum harmonic oscillator. It reduces the system to a kinetic energy term plus that critical quadratic potential, the x squared term. Because this quadratic approximation holds for any smooth minimum, solving this specific equation provides a template for understanding nearly every quantum system near equilibrium. Because we call it a harmonic oscillator, our classical intuition demands that the system must physically move. We expect something to swing back and forth. This assumption is a significant hurdle for students encountering quantum mechanics for the first time. Here is the paradox. If this mathematical framework is the quantum analog of a swinging pendulum, why is its probability density perfectly still? The answer is that the fundamental eigenstates of the quantum harmonic oscillator do not oscillate. They do not move at all. To see why, we need to deduce what these pure states look like, prove algebraically why they are frozen in time, and uncover the mechanism that makes classical motions secretly emerge. Correcting this intuition is required to understand quantum superposition. Solving the Hamiltonian traditionally means grinding through computationally heavy second-order differential equations, but there is a more elegant way. We can factor the Hamiltonian using a pair of mathematical tools called ladder operators, the raising operator, A+, and the lowering operator, A-. These operators are governed by a single canonical commutation relation. The commutator of A- and A+ equals exactly 1. This single algebraic rule dictates that the allowed energy levels of the oscillator form a rigid, equally spaced sequence. Each application of the operator moves the system exactly one discrete step up or down the ladder. This bypasses the continuous calculus of the Schrödinger equation. We derive the entire spectrum of states from pure algebra. The result is a series of discrete energy steps, a structure determined by the algebraic relationship between the operators, rather than any physical movement. These 4 spatial eigenstates reveal the ladder operator's work. Each energy step up adds exactly 1 node. The orange markers denote classical turning points, where particles normally reverse direction. Yet evanescent tails leak past these boundaries, showing a probability of existing in classically forbidden regions. These curves only show the spatial shape. To get the full time-dependent state, we multiply the spatial wave function by a complex phase factor, e to the -i ENT over h bar. But an instrument in a laboratory cannot read the wave function directly. It reads probability density. To find that, we apply Born's rule and take the squared modulus of this state. When we square the magnitude of that time-dependent complex phase factor, it cancels out completely. It equals exactly 1. This cancellation leaves a profound result. The probability density becomes purely spatial. The time variable vanishes entirely from the observable math. Single eigenstates are perfectly stationary. Even as the phase rotates, the physical probability holds perfectly still. Without mixed states, classical oscillation could not exist, which brings us back to the contradiction. If pure eigenstates are mathematically forbidden from moving, how does a classical guitar string actually vibrate? The secret to motion lies in combining states. We have to construct a quantum superposition. Let's create a state that is an equal mixture of the ground state and the first excited state. We write this as psi equals the state 0 plus the state 1 divided by the square root of 2. Next, we subject this new combined state to Born's rule, calculating its squared modulus to find the probability density. Expanding the square algebraically yields the individual densities of the 2 states, plus a new artifact, an interference cross term, which contains a cosine function. Look closely at that cosine function. It contains the time variable, t. This interference cross-term is the only part of the probability density that depends on time, making it the sole engine of movement in the system. Let's analyze the specific frequency of this new cross-term. The frequency is determined entirely by the difference in energy between the two superposed states, divided by h-bar. This beating interference frequency matches the classical macroscopic oscillation frequency exactly. When we plot this mathematical beating as a physical probability distribution over time, the packet of probability begins sloshing back and forth across e-axis. Notice how it behaves. This is not a rigid classical object sliding back and forth. It is a wave interference pattern that continuously shifts and deforms its shape as the relative phases of the two states drift apart. Without the mathematical reality of superposition, without two distinct states interfering with one another, the universe would be completely frozen. In this quantum mechanical description, oscillation is the observable consequence of interference between distinct stationary energy levels.